Welcome to Chapter 2, Quantum Spintronics. This chapter explores the quantum mechanical aspects of spin systems and their applications in quantum information processing. We'll learn about spin qubits, the fundamental units of quantum computation, and how they're implemented in various physical platforms. From semiconductor quantum dots to nitrogen vacancy centers in diamond, spin-based quantum technologies are advancing rapidly toward practical applications. A spin qubit uses the quantum spin state of an electron or nucleus as the basis for quantum information. Unlike classical bits that are 0 or 1, a qubit can exist in superposition, alpha times ket 0 plus beta times ket 1. The coefficients are complex numbers satisfying the normalization condition. This superposition principle, combined with entanglement, gives quantum computers their power over classical machines. Any pure qubit state can be visualized as a point on the Bloch sphere. The north pole represents ket 0, the south pole ket 1. The state is parameterized by polar angle theta and azimuthal angle phi. The equator contains equal superposition states like ket plus and ket minus. Quantum gates act as rotations on this sphere. This geometric picture provides powerful intuition for understanding qubit manipulation. Quantum gates are unitary operators that transform qubit states. The Pauli matrices X, Y, and Z are fundamental single qubit gates. X is a bit flip, Z is a phase flip. The Hadamard gate H creates superposition from a basis state. Arbitrary rotations around any axis can be constructed from these primitives. Each gate corresponds to a specific rotation on the Bloch sphere, enabling precise quantum state control. Quantum coherence is essential for quantum computing, characterized by relaxation times. T1 is the longitudinal or energy relaxation time, how long before an excited spin decays to ground state. T2 is the transverse or phase coherence time, how long superposition phase information persists. T2 star includes inhomogeneous effects. The relation 1 over T2 equals 1 over 2 T1 plus 1 over T phi connects these timescales. The Bloch equations describe magnetization dynamics, including relaxation. The transverse components mx and might decay with time constant T2 while precessing around the applied field. The longitudinal component mz recovers toward equilibrium with time constant T1. The trajectory spirals from initial state toward equilibrium. Spin echo techniques can refocus some dephasing, effectively extending coherence time for quantum operations. Understanding decoherence sources is crucial for improving qubit quality. Intrinsic mechanisms include spin-orbit coupling, hyperfine interaction with nuclear spins, and spin-phonon coupling. Extrinsic sources include magnetic field fluctuations, electric field noise, and charge noise. Dynamical decoupling pulse sequences, such as the Karp-Purcell-Mabungil sequence, can suppress slowly varying noise, extending effective coherence times by orders of magnitude. Semiconductor quantum dots confine single electrons in gate-defined potential wells. The electron spin serves as the qubit, with Zeeman splitting between spin states. Key advantages include scalability through semiconductor fabrication and electrical control via gate voltages. Isotope purification in silicon removes nuclear spins, dramatically extending coherence times. Integration with classical CMOS circuits is a major goal. Nitrogen vacancy centers in diamond are optically addressable spin defects with remarkable properties. The ground state is a spin triplet with a zero-field splitting of 2.87 GHz between the spin projection 0 state and the plus and minus 1 states. NV centers operate at room temperature with millisecond coherence times. Optical initialization and readout enable single spin detection. Applications span quantum sensing, quantum networks, and quantum computing. The NV center energy levels shift with applied magnetic field. The MS equals 0 state remains flat, while the plus and minus 1 states split linearly with field. This makes NV centers excellent magnetometers. By measuring the optically detected magnetic resonance frequencies, we can determine the local magnetic field either with nanometer spatial resolution using a single center, or with far higher sensitivity, down to the picotesla range, using a large ensemble at coarser resolution. The Hamiltonian captures this Zeeman-splitting behavior. Quantum entanglement is a purely quantum phenomenon where two qubits share correlations that cannot be explained classically. The four Bell states are maximally entangled two-qubit states. For example, phi plus is an equal superposition of both qubits in 0 and both in 1. These states violate Bell inequalities, proving quantum mechanics is fundamentally different from classical physics. Entanglement is the key resource for quantum computing and communication. Two-qubit gates create entanglement and enable universal quantum computation. The controlled NOT or CNOT gate flips the target qubit if and only if the control qubit is 1. The swap gate exchanges two qubit states. Together with single qubit rotations, CNOT forms a universal gate set. Physical implementation uses exchange interaction between neighboring spins, controlled by gate voltages or pulsed operations. Coupling spins to photons enables quantum communication and networking. The Jaynes-Cummings model describes a single spin interacting with a single cavity photon mode. The coupling strength G determines energy exchange rate. In strong coupling, where G exceeds both cavity and spin decay rates, reversible energy exchange occurs. This enables quantum state transfer between stationary spin qubits and flying photon qubits. Vacuum Rabi oscillations demonstrate coherent energy exchange between spin and photon. Starting with the spin excited and cavity empty, population oscillates between spin and photon with period pi over g at resonance, complete transfer occurs. When detuned, oscillations are faster but incomplete. These oscillations are the hallmark of strong coupling and enable controlled quantum state transfer between different physical systems. The Kitaev chain is a model for topological superconductivity hosting Majorana zero modes. These are exotic quasiparticles that are their own antiparticles. In the topological phase, where the magnitude of the chemical potential is less than twice the hopping amplitude, zero-energy Majorana modes appear localized at the chain ends. Their non-abelian statistics and topological protection make them promising candidates for fault-tolerant quantum computing. Majorana zero modes are localized at opposite ends of the topological chain, with wave functions decaying exponentially into the bulk. This spatial separation provides topological protection. Local perturbations in the middle cannot affect the edge modes. Information encoded in Majorana pairs is stored non-locally, making it immune to local noise sources. This could enable qubits with inherently long coherence times. Let's review the key equations. The qubit state on the Bloch sphere uses polar and azimuthal angles. Relaxation times are connected through T-phi, the pure dephasing time. Bell states represent maximum entanglement. The CHSH inequality distinguishes quantum from classical correlations. The Jaynes-Cummings Hamiltonian describes spin-photon coupling. These equations underpin quantum spintronic technologies. We've explored quantum spintronics from qubit fundamentals through advanced topics. Spin qubits visualized on the Bloch sphere, coherence characterized by T1 and T2, platforms ranging from quantum dots to NV centers. Entanglement and Bell states enable quantum advantage. Spin-photon coupling connects to quantum networks. Topological Majorana modes offer protection. Next, in Chapter 3, we'll learn computational methods for spintronics research.